Hey, welcome back. We're going to continue our discussion of the applications of the gradient and how it can give us the steepest rate of increase off a level surface. So the gradient vector, now if we have to look at the gradient vector of f of xy, now remember this is dealing with a three-dimensional figure. It's going to be the gradient vector of a three-dimensional figure is going to be orthogonal to every level curve. Now, basically, with that at the point xy, so of course we're looking at a two-dimensional level curve. So from a three-dimensional surface, the level curves, remember, are 2 dimensions. So, for example, let's say our level curves are a bunch of circles. The gradient vector is always going to be orthogonal or perpendicular to at every point on those surfaces. And it doesn't really matter what that level curve looks like, even if it's curvy. All that basically means is that we are going to go in multiple directions as we move along that surface. So the gradient vector is always going to be orthogonal or perpendicular to every point on that level surface. In a four-dimensional graph, like right here, del f of x, y, z, in a four-dimensional graph, our level surfaces are three-dimensional, but the same idea. At every point on that surface, our gradient is going to be perpendicular. So like if our gradient, let's say, is let's say like a cone or a paraboloid, at every given point, we are always going to be perpendicular to that surface at any given point. And that's what the gradient does for us. And we talked about, well, what does this do for us in the previous video? Well, remember from earlier this year, if I can find my gradient, I can now find the equation of our normal line. Well, also we talked about in Unit 1 here, go back to the older videos, that if we have a perpendicular line to a surface, we can find the equation of that tangent plane. So these are lessons that we talked about earlier this year. Of course, this was using that cross product, dot product combination right there. So there's a wonderful video on that. Go take a look at that. So let's go ahead and take a look at how we can use the gradient to find our equation of our tangent plane and our normal line. So there are two types of equations that we have. Of course, one, we have an implicit equation, and we have, of course, an explicit equation. An explicit equation is already kind of solved for. It could be something like f of x, y is equal to x squared plus y squared. An implicit equation is where an equation is not really solved for, and that's the example we're going to take a look at right here. If our equation is implicit, such as it's x squared plus y squared minus z squared equals 9, we are going to convert it to an explicit function. And 2, we need a point, which they give us, 3, 0, 0. So to get the direction vector, we're going to use our gradient. And of course, that's just 2x, 2y, negative 3z squared. Now, I'm going to find my direction vector at the point. So, del p of 3, 0, 0, and that's going to give me 6, 0, 0. Now remember, this is my direction vector. And earlier this year, when we wrote the equation of a plane, this was our A, our B, and our C when we wrote the equation. The point they give us is 3, 0, 0. So to write the equation of our plane, if you forgot how to write the equation of a plane, here it is. It's A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught, equal to 0. And I can write my equation of my plane now. This is going to become 6x minus z, erase that, 6x minus 3 plus 0, y minus 0, plus 0, z minus 0, equals 0. Remember, there's our x naught, y naught, and our z naught right there. And when we solve this, we would just get 6x minus 3 equals 0, and that would be the equation of our plane. Again, if you forgot how to write the equation of a plane, look back in one of my earlier videos. You can see that. Go over that again. All right, so let's go ahead and find the equation, find the normal line to our surface right here. Now we're looking for the equation of a normal line. So remember, we are going to use parametrics. To write the equation of a line in 3 dimensions is very tough. We're going to use parametrics or symmetric. We're going to use either one of those. Remember, it's really hard to write the equation of a line in rectangular form. So the first thing we need to do is we need to get our directions. So to do that, we need our gradient. So I'm going to write this, of course, as z equals x squared minus 4xy plus 2. And I'm going to write this as my another equation, p of x, y, z. See, now I'm in 3 space. Now I'm talking about now I'm being able to get my level surfaces, right? X squared minus 4xy minus z plus 2. So let's review our symmetric form. In symmetric form, remember the equation was x minus x naught over a equal to y minus y naught over b equal to z minus z naught over c. Remember, the a, b, and c were the direction, was from my direction vector. And since I want this to be normal to the surface, I know this is going to be my gradient because we want perpendicular. Since I want perpendicular, my direction vector will be my gradient because the gradient, remember, will find the vector orthogonal to the level surface. So we're going to be looking at the gradient here. So let's go ahead and find our gradient, and of course we have our point 2. The point, right, that was just the x naught, y naught, z naught, and again, they give us that. So let's go ahead and solve this. The first thing we need to do is our gradient. That becomes, be careful in terms of x, so that's 2x minus 4. In terms of y, negative 4x, and z, negative 1. Find the gradient at the point 1, 1, negative 1. Remember, what this is going to give for us is our direction vector. Plugging in the 1, this is 2 minus 4, so negative 2. 1, that becomes negative 4, negative 1. So my line, my symmetric line, remember this is going to give me the direction of max increase, right? This is our direction of max increase off the surface. Therefore, this is going to be perpendicular to the surface. So that's my direction vector right here. So here we go. Where are we going to write? There it is. It's going to be x minus my point. Well, my point is x minus 1 over a. Well, we just said a was negative 2 equals y minus 1 over b. There's my a, there's my b, there's my c. 4 equals z plus 1, because it's a minus, all over c, which is negative 1. And there's our symmetric equation for our line, of our normal line. So this will be perpendicular to the surface at the point 1, 1, negative 1. All right, go on to video number 3. We'll take a look at a few more examples. I'll see you soon. Bye.